Okay, so we're going to start with Chapter 4, Section 6, Counting Methods. And if you recall, we talked about probability in class last time. In order to kind of explore probability a little more deeply, we have to be able to count the number of ways things can occur. So finding the total number of outcomes or ways things can occur is a challenge that we're going to use some different techniques to accomplish. So the simplest situation is where you have a task or outcomes where there's only one part to it. So a simple example would be like flipping a coin and getting heads or tails, or rolling a die and getting a 1, a 2, a 3, a 4, a 5, or a 6. In those cases, it's pretty simple to just list out the possibilities. So for example, if there's a club, I'm just going to call it N, but I mean, it's some club at school, and there's 4 members in the club, Mike, Adam, Ted, and Helen. In how many ways can this group select a president? You can literally just list out, Mike, Adam, Ted, and Helen. So there's 4 possible ways to have a president chosen. But it gets more complicated when we have more parts to the task. So for an example of a 2-part task, what if we wanted to construct 2-digit numbers written from the set of digits 2, 4, 6? So what I mean by a 2-digit number would be something like the number 42, which would be different, by the way, from the number 24. So this task can be thought of, and I want to make this clear. You don't have to, 2 people don't necessarily think of a task as being broken down in the same way. But in this case, it's a pretty simple scenario. You can just think of it as choosing the first digit and then choosing the second digit. So we have several options for each. Whenever you have a 2-part task, an easy way to kind of draw a picture of what your options are is a product table. So this is just like in school when you did multiplication tables, except you're not multiplying. So for example, here I've drawn a product table that's going to represent the results on the 2 dice. And we have the first digit and the vertical side on the left, and then we have the horizontal second digit going across. Each one can be a 2, a 4, or a 6. So we have the case where the first digit and the second digit are both 2s, so 22. And then 2, 4, so 24, 26, and so on, continuing throughout the whole chart. We get all the different possibilities. So we can count the number of ways this happens. There's going to be 9 possibilities. It's a 3x3 chart, notice. So 3 times 3 is 9 different possibilities. Another scenario where you would have 2 parts to the outcome, 2 parts to the task, would be rolling a pair of dice. We'll think of them as distinguishable. So imagine 1 red die and 1 green die. We talked about this in the probability section as well. Whenever you see a question about dice or 2-part tasks in general, if the number of outcomes is small enough, having a nice little product table really helps to clarify what you're thinking on your counting. So here we have, for example, rolling a die on the rolling a red die and getting 1 through 6, rolling a green die getting 1 through 6, all the possible different outcomes. So for example here, let me see if I can highlight that. Hold on. I'm not seeing my tools. Okay, so here would be the case where we got a 2 and a 6. A 2 on the red die and a 6 on the green die. Now, let's assume that we want to use systematic listing to determine the number of ways you can roll a total of 8. 2 plus 6 is 8, so that would be one of the events that would have that result. We also have 3 plus 5 would be 8, 4 plus 4 would be 8, 5 plus 3 would be 8, and 6 plus 2 would be 8. So none of the others are going to add up to 8, right? So we can real quickly see that there are 5 possible ways to get a total of 8 on the 2 dice. So back to that club N that we talked about earlier with Mike, Adam, Ted, and Helen. Find the number of ways that they could elect a president and a secretary. So earlier we just asked about the number of ways to get a president, and there's only 4. But when you add in that second part of the task, then it complicates it a little bit. But you can, good morning, Jessica. Thanks for posting. You can figure that out again with a product table. 2-part task, you can use a product table. So the 2 parts that I'm referring to, by the way, are choose a president and choose a secretary. So here's the product table that we could draw. All right, so president options, M-A-T and H, secretary options, M-A-T and H. So in this case, when we look at, say, this square with AM in it, what is that saying? That's the scenario where the president would be A and the secretary would be M, which would be different from MA, right? Where the president is M and the secretary is A. Now, in this particular case, on this product table, we actually have to cross off repetitions because we're not going to have the same person be both president and secretary. So we're actually listing some impossible situations. So let's just cross those off. And then we see that what we have left out of the 4x4 grid, which 4 times 4 is 16 possibilities, we removed 4 of them. So that means we have 12 left. So 12 possible outcomes of choosing a president and a secretary. Now, this should not be confused with the scenario where you're just picking 2 people to be on a committee. The difference here is that on a committee, everybody's doing basically the same job. So, you know, we're not distinguishing between a president and a secretary. We're just going to have 2 people doing the same thing. So how does that change the scenario? We still can't have repetitions, but the order of the letters isn't going to make a difference. That's right, Jessica. 2 of the squares, she asked, so it will be 2 different ways to get the same answer. Yeah, exactly. So we no longer really have a president. Oops, I'm trying to get my ink going here. So we really just have 2 equivalent people. So A and M and A really mean the same thing. Okay, so we're going to cross off our repetitions, but we also are going to cross off half of our grid because all of those are really the same as those on the other side. So we're going to have left how many? Just M-A, M-T, M-H, A-T, A-H, and T-H, so 6 of them. Okay? So be careful when you make your product table. You have to pay attention to context and make sure you're not overcounting. Okay, another way we can count tasks, multiple part tasks, I should say, is to use a tree diagram. So when we get past a 2-part task into a 3-part task or a 4-part task, you can't really use a product table because it only has 2 dimensions. So an alternative is a tree diagram. So here's a scenario where we have a 3-part task, building numbers from a set of digits. So we're asked to list the 3-digit numbers that can be formed from the digits 1, 2, and 3 if repetition is allowed. That's an important statement because if repetition is not allowed, for example, we would not be including the number 111. So what I'm going to do is I'm going to make 3 columns, 1 for the first digit, 1 for the second digit, and 1 for the third digit. And for the first digit, I'm going to draw branches that represent my 3 different options. The first digit could be a 1, a 2, or a 3. But since repetition's allowed, I still have 3 options for the second digit, even no matter which 1, 2, or 3 I picked for the first digit. So just to be clear here, oops, let me go back. Trying to get my ink going. It's giving me problems. Okay, so just to be clear here, if you can see this, if I highlight one branch, for example, this branch here, this is the branch that corresponds to any scenario where the first digit is a 2 and the second digit is a 1. Now we also need to pick the third digit, but no matter which of those previous branches have occurred, we have still 3 options for the third digit. So it gets to be a lot of branches. And obviously our goal is really to get to a different way besides drawing these big pictures. But this kind of will help you understand that different way. So that's why we're going through it. So in this case, if I extended maybe down this branch here, and by the way, people seem to find it easier to read the branches going backwards from the end. So what I mean by that is if you want to follow a particular branch that ends at this 3 here, if you follow the branches backwards, not trying to start at the beginning where the 2 was, but going back in this direction, there's only one possible path. So it's a lot easier for your eyes to follow along. So anyway, this particular branch represents what 3-digit number? If Jessica or Yolanda might still be here. Do you know what that number would be? Highlighted in yellow. Very good. It does have the digits 3, 1, and 2, but the reason I said to read it backwards was not because it's the number 312. It's because it's just easier to follow along that branch. It's actually the number 213, and the reason why we know that is because the first digit column is above the 2. And the second digit column is above the 1, and the third digit column is above the 3. So this is actually representing the number 213, just because of the way we've labeled our columns. Okay? So we chose to pick our first digit first, then our second digit, then our third, so that's 213. Hi Maria, welcome. Okay, so that top branch then would be the number 111. I hope you can see that, it's kind of tiny. The next branch would be 112. The next branch would be 113, and so on. The next branch would be 121, and then 122, 123. Notice that we've done all the 3-digit numbers starting with 1, 1, and then all the 3-digit numbers starting with 1, 2. And next, we have all the 3-digit numbers starting with 1, 3. So it's a very organized way or systematic way of listing out the numbers, systematic listing. And there are the rest of the branches. Okay? Okay, let's try a slightly different scenario. Find the number of 3-digit numbers that can be written using the digits from the set 2, 4, 6, assuming repeated digits are not allowed this time. Okay, so we're still constructing 3-digit numbers. The significance of that is that it's a 3-part task. So at this point, the only method we know for coming up with how many of those there are is to use systematic listing, and a tree diagram is a good way of organizing that. Not the only way. So what I've done here is, again, first column has the 2, the 4, and the 6. But look at the difference, how much smaller this chart is, how many fewer branches. That's because the digits are not allowed to repeat. So, for example, when we have the first digit being a 2, right here, okay, then we know that the second digit can't be a 2. It could be a 4 or it could be a 6, but it can't be a 2. Now, once we know that the first digit is 2 and then 4, the third digit can't be either 2 or 4, so the only possible digit left is 6. And then if it's 2 and 6, then the only possible digit left is 4. So that's why this doesn't grow so big as the other tree diagram, where we still had 3 possibilities at each level, at each part of the task. So the first branch turns out to be 246, the second branch 264. Okay, now this branch down here, this is all the numbers that start with 4. And so if it starts with a 4 and there's no repetition, it has to be either 2 or 6 as the next digit. But if it's a 2, then the third digit has to be a 6 since no repetition is allowed. And on the other hand, if it were a 6, you'd have to have a 2 for the third digit. So that's where we get 426 and 462. And then finally, it could have been that the first digit was a 6, in which case the second digit could only be a 2 or a 4. In the case that the second digit was a 2, that only leaves a 4 for the third digit, and if the second digit was a 4, that only leaves a 2. So we get the 3-digit numbers 624 and 642. So altogether, there are exactly 6 possibilities. A lot fewer than the previous slide where we had 27 different possibilities because repetition was allowed. Okay. I'm going to try to make the words bigger on this slide here. Hold on just a second. By the way, feel free to interrupt me if you have any questions. Just post them in the chat. All right, so here's a question. It says, Arnie, Bobette, Chuck, and Deirdre have tickets for 4 reserved seats in a row at a concert. In how many different ways can they seat themselves so that Arnie and Bobette will sit next to each other? All right, so by the way, just to give you a little preview, we might want to know the probability that they end up sitting next to each other if they sit down randomly or something like that. Our goal is to be able to use counting for probability. Anyway, we're going to refer to these people as A, B, C, and D. And what we want is them to sit down so that A and B are next to each other. So we have a little bit of a stipulation there that we have to keep in mind, but we still have a multi-part task. It's 4 parts because we have to sit someone in the first seat, someone in the second seat, someone in the third seat, and so on. So what we're going to do is list out the parts: first seat, second seat, third seat, fourth seat. And then we're just going to go through the different options. So either A sits down, B sits down, C sits down, or D sits down. Okay, so up to that point, that's all that we need to do is just list out A, B, C, or D could sit in the first seat. But once that first person is seated, we need A and B to be next to each other. So when we're sitting the next person, if it was A in the first seat, then it has to be B in the second seat. Now, once we seat that second person, we have all of our options again. So A and B have been seated. That leaves C or D for the third seat. And then if C sat down, D would be in the fourth seat. But if D sat down, C would be in the fourth seat. Okay? And then what happens if B is seated first? Well, we still need A and B next to each other, so we still have only one option, and that would be for A to sit down. But then once those two are seated, we have either C or D could sit down, and again, once the first three people are seated, you only have one option for that fourth person. All right, now, what if C sat down first? If C sat down first, then we still have three possibilities. A, B, or D could all sit down next. But if A sits down next, B has to sit in the third seat. If B sits in the second seat, then A has to sit in the third seat. And in either case, that only leaves person D for the fourth seat. On the other hand, if after C sat in the first seat, D sat in the second seat, then we have two options. We could have A or B sit in the third seat. But once again, once they sit down, A and B have to be next to each other. Plus, there's only, that one person left to be seated. Okay? Now, before I show you the chart for person D sitting first, just try and think, maybe jot down on a piece of paper what you think that last branch or branches would look like. Do you have something written down? If you're not sure, just guess, and we'll see if your instincts match up with, the way that it's supposed to work. Okay, so if D sits down, how many options do we have left for the second seat? So we still could seat anybody, right? There's nothing telling us who needs to sit next to person D. So it could be A, B, or C. But once person A is seated, we know that B has to sit next to them. And if B is seated, A has to sit next to them. And then that's only going to leave person C for the fourth seat. Now, if person C is seated in the second seat, which is that last branch down here, then we still have some flexibility because A or B could sit next. We weren't told that C had to sit next to anybody in particular. But if A sits next, B is the only person left, and if B sits next, A is the only person left. Okay, so all together here, well, let's practice reading the branches. So what does that branch that ends, the first branch at the top that ends with a D, what scenario does that represent? That represents the scenario. Let's highlight it so you can see it a little bit better. So I highlight from the end just because it's easy to find my way back, but you read from left to right. So we have what? A in the first seat, B in the second seat, C in the third seat, and D in the fourth seat. A, B, C, D. All right, now let's highlight the next one. So again, I'm highlighting from the end just because it's easier to keep track that way, but you read from left to right. So this one has A in the first seat, B in the second seat, D in the third seat, and C in the fourth seat. Okay, the third one would be B, A, C, D. Let's highlight that one. Okay, and then what do you think the next one would be? Can you type it into the chat line? The reason why I'm asking is because a lot of times people have trouble just reading the diagram at first. Once you get used to it, it's not so bad, but at first, it just makes everybody's eyes cross. So What do you think? Jessica, Maria, or Yolanda? If any of you are there, can you take a guess as to the seating arrangement that's represented by the next branch? BADC. Good job. Let's see, who was that? Was that Yolanda? I think so. Yeah. So Yolanda got it right. It's BADC. And then we have CABD, CBAD, CDAB, CDBA, DABC, DBAC, DCAB, and DCBA. So we have a total of 12 arrangements. Okay, now this last scenario is different from the other two we saw in a very particular way. There is a certain criteria that will help us to take a shortcut. Shortcuts are good, right? We don't want to have to draw out these tree diagrams all the time. So what we're going to do is we're going to look for what's called uniformity in multiple part tasks. And all that means is that no matter which choices were selected for previous parts, the number of choices is going to be the same. So, for example, which of the following tree diagrams represents counting of a multi-part task with uniformity? Diagram 1, which we just constructed a minute ago, or diagram 2, which was, this is actually a diagram representing the number of 3-digit numbers that you can construct from the digits 1, 2, and 3 if repetition is not allowed. All right, so again, what is uniformity? That means that no matter what has happened in the previous step, we have the same, or previous part of the task, we have the same number of options for the next part of the task. Notice that in diagram 1, it depends on who sat down. If we think of the A, B, and C being seated in the 4 seats, it depends on if A and B were seated or if C or D were seated. If A or B were seated, we only have one choice for what's going to happen in the next part of the task. But if C or D were seated, we had 3 options. On the other hand, if you look at diagram 2, going from the first part of the task to the second part, no matter whether we picked a 1, a 2, or a 3 for the first digit, we're going to have 2 options for the second digit. So it looks like the screen might be a bit blurry, huh? I'm having trouble getting my bit rate up. Sorry, guys. Okay. So hopefully you can see it well enough to see that the one diagram has uniformity and the other one does not. Which diagram, diagram 1 or diagram 2, has uniformity? Very good. Diagram 2 has uniformity because it doesn't matter, and it's not just at the first, going from the first part of the task to the second, but also from the second to the third. No matter which choice was made, we only have one option there. So the number of choices was different depending on the previous choice in diagram 1. That violates uniformity. So only diagram 2 is uniform. Okay, the reason this is important is because it's going to allow us to take a shortcut called the fundamental counting principle. And that shortcut says that if you have uniformity, then you can find the number of ways a multiple part task occurs by just multiplying the number of ways each part of the task occurs. So if the first part occurs in n1 ways, and the second part occurs in n2 ways, and the third part occurs in n3 ways, and so on, you just multiply those numbers up and you get the total number of ways something can happen. So for example, in this uniform diagram that we saw in the previous slide, notice that there were 3 ways to choose the first digit, there were 2 ways to choose the second digit, and then only 1 way to choose the third digit once the first 2 were chosen. Again, because repetition wasn't allowed. But in any case, it's uniform. There's no difference. It's not as if when a first digit was a 1, we had 2 options, but when the first digit was a 2, we only had 1. No, we always had the same number of options going from one part of a task to the next. So that's uniformity, and what uniformity is saying is that we can multiply 3 times 2 times 1 and get 6 possible outcomes, which is exactly what we observed in the tree diagram. Now the tree diagram's nice because you actually can list out all the options, but if you don't need to know all the options, have them explicitly listed, you just need to know how many, you can just skip all that. And by recognizing that there's uniformity, you can just multiply the number of ways to do each part of the task. So for example, if I asked you how many 2-digit numbers can be made from the set 0, 1, 2, 3, 4, and 5, we could use this method rather than a product table. By the way, whenever I say a 2-digit number, a 3-digit number, or so on, you can't have a 0 as the first digit, okay? Because then it would become a 1-digit number, basically. 0, 1 would just be 1, right? So in any case, we're going to break the task down into 2 parts. The 2 parts are going to be choosing the first digit and choosing the second digit. And we're going to just think, okay, how many ways could I select the first digit? Now, since you're not allowed to use 0, that only leaves 5 other options, right? So the first digit could be a 1, a 2, a 3, a 4, or 5. So there are 5 options there. Now, this is important when you're thinking about this. Does it matter what I chose for my first digit? Does that affect in any way the second digit? So, for example, if it said repetition was not allowed, then we'd have to take that into consideration. But it doesn't, and so we never assume any extra restriction other than what's explicitly stated. So how many options do we have for the second digit? Well, it can be a 0, right? For example, the number 20 is a 2-digit number that ends in a 0. So there are 6 possibilities for the second digit without any concern for what the first digit was. We're confident there are 6. So that means there's uniformity because it doesn't vary going from the first digit to the second. There's always 6 possibilities. So we can apply the fundamental counting principle and say there are 5 times 6 equals 30 2-digit numbers. So the fundamental counting principle is a really nice shortcut. Let's take a look at a different example. Please, let me know if I'm going too fast. How many 2-digit numbers that do not contain repeated digits can be made from the set? Okay, so when you see an extra little stipulation like that, you have to take it into consideration. It might affect uniformity or it might not. But we're still going to just break our task down into 2 parts, selecting the first digit and selecting the second digit. So how many ways can we select the first digit? Well, once again, you cannot have 0 as a first digit in a number, so you always leave that out. So there's still going to be 5 ways to choose the first digit, a 1, a 2, a 3, a 4, or a 5. Now, but the second digit, how many digits are left in the set to choose from? Well, we definitely could use the number 0, okay? That is allowed to be a second digit because we know that it wasn't the first digit. But one of these other numbers is gone. So let's say, for example, we used the 3 as our first digit. That would mean that we couldn't use it as our second digit. Or, so that would mean there would be 1, 2, 3, 4, 5 options left. What about if we used the 2 for our second digit? Well, if that were the case, then we would just take the 2 away, and how many options would we still have? The 0, the 1, the 3, the 4, and the 5. We would have 5 options again. In fact, no matter which one of these digits, 1 through 5, that I used in the first digit, when I take it out, that still leaves 5 possibilities for the second digit. Okay, so we are basically just removed the whatever digit we used in the first part of the task. We removed it from the possibilities, and now 5 times 5 is 25 possible 2-digit numbers. How many ways can you select 2 letters followed by 3 digits for an ID tag? So this has many parts to the task, right? So we have to choose the first letter, the second letter, and the 3 digits. By the way, in the fundamental counting principle, the order matters in the sense that your count, you have a first and a second, or you have different categories. So that's going to be important later on, so I just want you to keep that in the back of your mind. An ID that was AB123 would be different than an ID that was BA123, but the fundamental counting principle accounts for that. So how many letters are there in the alphabet that we could use for our first letter? How many letters are there in the alphabet? "26, right? Now it didn't say repetition's not allowed, so we just assume that it is. So that would also be 26 letters we could choose from for our second letter on our ID. So it could be AA or BB, that's fine. And then digits. How many digits are there in our base 10 number system? There's 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 10 digits. And zeros are okay. They didn't say we couldn't use zeros. So there's 10 possibilities for each of the digits on the ID. So the fundamental counting principle says, since we know for sure, notice how as I was filling that in, I had no doubt, regardless of what happened with the previous letter, I knew how many options there were going to be. You'll know when uniformity is violated because you're going to not be able to answer that question. You'll know because you go to look at the next part of the task and you ask yourself, how many ways can that happen? And you'll realize, oh, that depends on what I did in the first part of the task. Okay, so we have uniformity, so we're just going to multiply. 26 times 26 times 10 times 10 times 10 is 676,000 IDs possible. A lot of IDs, right? Okay, so this would be something that would be good if you could just pause for a minute and try to answer these questions for yourself real quick before I talk about it. It says, how many 3-digit numbers are there in our system of counting numbers? And how many odd, non-repeating 4-digit counting numbers are there? So how many 3-digit numbers are there in our system of counting numbers? That would be something I hope you could probably take a good guess at right now using the fundamental counting principle. But that second question, you can see how complicated it can get. So we'll discuss that one together. But real quick, how many 3-digit numbers are there in our system of counting numbers? So remember, just as a hint, if you're going to use the fundamental counting principle, which isn't the only way, but if you're going to use the fundamental counting principle, you're going to want to think about the number of ways to pick the first digit, number of ways to pick the second digit, and the number of ways to pick the third digit. And the basic digits in our number system are 1, 2, 3, 4, 5, 6, 7, 8, and 9. And of course, we can never have a 0 in the first digit. Okay, so jot down how many ways you think the first, second, and third digits could be chosen. Let's see what you get. Good, Maria. She said 9, 10, and 10. So there's 9 digits, 1 through 9, for the first digit. And since repetition is allowed in our system of numbers, there's 10 and 10, 0 through 9 for each of the second and third. So 9 times 10 times 10 is 900 counting numbers that have 3 digits in our system. Now, there's another way you could do this without using the fundamental counting principle. We know that the 3-digit numbers go up to the number 999. And so from 1 through 999, there are 999 numbers. 1 through 99, there are 999 numbers. But we don't want to include the 2-digit numbers. So I'm going to take away the numbers 1 through 99, which there are 99 of those. And if you subtract that, you're going to get 900. So that's a perfectly valid way to determine how many 3-digit numbers there are in our system of counting. But I wanted to demonstrate how the fundamental counting principle works. Okay, now let's look at this next one. How many odd, non-repeating 4-digit counting numbers? Okay, so before we try to count this, I just want to write down a number that would fit that description. So it's got to be 4 digits. It's got to be odd, meaning the last digit has to be odd. So the last digit has to be a 1, a 3, a 5, a 7, or a 9. It has to be non-repeating, okay? So maybe I could have the number 2, 3, 4, that's 3 digits, and then a 1 to make sure it's odd at the end. So this would fit that description. It's odd because the last digit is odd, and then it has 4 digits altogether, and none of them are the same, so it's non-repeating. Okay? All right, so with that, kind of picture that in your head. Now we have to decide how we're going to break up the problem into tasks. And as I mentioned before, there's not necessarily just one way to do that. But let's say we wanted to pick our first digit, our second digit, our third digit, and our fourth digit. So when we go to pick our first digit, there's only one restriction, right? We can use any digit we want out of the set 1, 2, 3, 4, 5, 6. So that means there are 9 possibilities, just like in the previous example. Oh, technical problems. Oh, we're back. Okay, for a second I lost the stream. Sorry about that. So what I was saying is, as with the previous problem, we could have 9 possibilities for our first digit. Now, with the second digit, we know that we can't have the same digit that was in the first digit. So like in the previous problem, we could reason, well, okay, it could be 0, and it could be 1, 2, 3, oops. All the way up to 9. Oh, good question, Maria. She asked, why did I use a 2 and a 4 in this number if it's supposed to be odd? And the answer to that is, in order for a number to be an odd number, it just has to end in an odd digit, right? So remember, even and odd are just alternating in our number system. So the number 1 is odd, the number 2 is even, the number 3 is odd, the number 4 is even, the number 5 is odd, the number 6 is even, the number 7 is odd, the number 8 is even, the number 9 is odd, the number 10 is even. Notice 10 has a 1 in it, which is an odd number, but it ends in 0, so it's considered even. The number 11 is odd, the number 12 is even. So anytime a number ends in an even digit, it's even. Anytime it ends in an odd digit, it's odd. Number 13 is odd. Number 14 is even. Number 15 is odd. Number 16 is even. That was supposed to be a 4. Number 17 is odd. Number 18 is even. Number 19 is odd. Number 20 is even. Number 21 is odd. Ends in an odd number, even though it has a 2 in it, it's considered an odd number. So did that answer your question, Maria? I'm gonna erase this because it's a little messy here. Oops. Okay. All right, so let's go back to thinking about what our second digit would be. The first digit we had, remember, anything, it could be anything but 0. But the second digit, since we don't have repetition, we would have to leave out one of the digits 1 through 9. So we would have 8 of these that we could still use, plus we'd have the number 0 that we could still use. So we have 1 there. So we have 9 possibilities for the second digit. For the third digit, we have now used 2 of the numbers, either the 0 or another number from 1 through 9. So we had 9 in the last step. Now we're down to 8 because we can't use whatever we used for the second digit or the first digit. We're down to 8. Now, here's a problem. The fourth digit has to be odd. How many odd numbers are left? We have no idea because we could have used all odd numbers up to this point, right? We could have had a 1, a 3, and a 5, and in which case the only odd numbers that would be left would be 7 and 9. Or it could be we used all even numbers up to this point. We had chosen a 2, a 0, and a 6. And so we actually still have 1, 3, 5, 7, and 9, all 5 of the odd digits left. That means we are violating uniformity. But the interesting thing is that we can actually solve that problem. We can fix our uniformity problem by just rearranging the order in which we do our tasks. So uniformity can sometimes be fixed just by rearranging the tasks. So I'm going to rework this problem a different way. This time, since the problem was not knowing how many odd digits I had for my fourth digit, I'm going to pick that first. I'm going to pick my fourth digit, then my first digit, then my second digit, then my third digit. And let's see if that fixes the problem. The fourth has the most restrictions on it, so that's why I'm going with that one first. All right, so for the fourth digit, which options do we have? It has to be odd in order to make the whole number odd. So we have to use a 1, a 3, a 5, a 7, or a 9. So there are 5 possibilities for the fourth digit. For the first digit, we can use any number except for 0, right? But we've used one number and we're not allowed to have repetition. So out of the 10 digits, 0 through 9, there were 10 digits altogether. We've used one of them already. We've reserved it for the fourth digit. So there are going to be 9 left, but we can't use the 0. By the way, I know I didn't use the 0 for the fourth digit because that is, sorry, messages are popping up here. We know we didn't use 0 for the fourth digit because it's not an odd digit. So that means that we have left out of here, out of the 9 that were left, we take out the 0 and there are going to be 8 left. So this first digit, we have 8 possibilities. Now, for the second and third digit, we don't have that 0 restriction. So all we know is we've picked some odd digit for the fourth and we've picked some non-zero digit for the first. And now that leaves, out of the 10 digits total, we still have 8 left. And then for the third digit, we still have to take into consideration that we've used 3 distinct digits at this point that we can't use again. So that means that out of the 10 digits overall from 0 through 9, there's 7 left. So 5 times 8 times 8 times 7 would be a product that would give us the number of 4-digit counting numbers. Let's see, what does that turn out to be? $2,240. Okay, any specific questions about that one? Okay, so that one's pretty tough, but I wanted you to see what the possible, what possible scenarios can come up. All right, so in a lot of the problems, when we apply the fundamental counting principle, when we don't have repetition, we end up having to multiply, say, 5. Oops, that's crazy. Look, hold on. We end up having to multiply like 5 times 4 times 3 times 2 times 1. So since this is a common calculation, multiplying all the numbers starting at one number going one less each time all the way down to 1, we have a shorthand for that. 5 times 4 times 3 times 2 times 1 can be written as 5 with an exclamation mark. That's read as 5 factorial. So we have a definition here for any counting number n. The product of all the counting numbers from n down through 1 is called n factorial and is denoted n with an exclamation mark. Okay, make sure to note that your calculator does have a factorial option on it. Let me see if I have a picture of that for you. No, I don't. Maybe it's in the next slide. No, I don't. Okay, so let me just tell you, if you're using the TI-30X2S calculator, TI-30X2S, and you wanted to calculate 5 factorial, instead of typing in 5 times 4 times 3 times 2 times 1, let me see. What you do is you type in 5, and then you find the key that says PRB on it. That stands for probability. It has a bunch of calculations in it that you can use. When you push that button, you're going to see NPR and NCR, and then an exclamation mark on your screen. The NPR will be underlined, but you want to underline the exclamation mark. So you're going to arrow to the right. You know how there's those 4 arrow buttons on the upper right side of the buttons? So arrow to the right until you see that the exclamation point has been underlined. And then you hit enter. And then what you'll see on your screen is 5 factorial. Make sure to hit enter. Then you see that 5 factorial and you're going to hit enter again. And you get 120. Was everybody able to find that on your calculator? Let me know if not, okay? If you're using a calculator other than the TI-30X2S, then I can probably help you find the manual for your calculator if you just tell me at class tomorrow. They're pretty much all online now. Okay, so that's how we calculate a factorial on our calculator. I'm going to write them out by hand here just to be clear. So 4 factorial, you can calculate on your calculator, but it's 4 times 3 times 2 times 1, which is 4 times 6 or 24. So if you type in 4 factorial on your calculator, you should get 24. Be careful if you have something with parentheses like this one. 4 minus 1 comes first before the factorial. This does not equal 4 factorial minus 1 factorial. So you're going to just say 3 factorial, which is 3 times 2 times 1, which is 6. And then here we have 5 factorial over 3 factorial. You cannot do any operations with the 5 and the 3 until you've worked out the factorial part. So now one interesting thing is some of these get so big that your calculator can't even do an exact calculation. You might actually be able to do a better job by hand. What I mean by that is here we have 5 times 4 times 3 times 2 times 1 in the numerator, and in the denominator 3 times 2 times 1. So you have all these common factors that cancel out, and 5 times 4 is just 20. Okay, so stop me if you get stuck on anything. We're going to use these factorials to do some other shortcuts other than the fundamental counting principle, even shorter sometimes. Okay, now by definition, 0 factorial is equal to 1. You might remember from exponents, anything to the 0 power is 1. That association might help you remember, but if you forget, guess what? Your calculator knows. So you can find 0 factorial on your calculator, and it'll tell you it's 1. All right, now let's talk about the number of ways to arrange a set of objects if you use all of them. So for example, if we wanted to find the total number of ways to arrange 5 students in a row, so we know all 5 students are seated, but we just want to count the number of ways to shuffle them. So it's 5 factorial, and the reason is because we have 5 options for who sits in the first desk. Then once that person's seated, they can't be seated again, right? You can't put their clone next to them in this scenario. So we're going to have 4 students left for the next desk, 3 for the next, 2 for the next, and 1 for the next. So fitting 5 students, arranging them into 5 desks, we have 5 factorial. In general, if you have n objects and you want to arrange them into n possible positions, that's n factorial. So if I asked you how many ways can you line up 6 different books on a shelf, well, you could go and do the fundamental counting principle, and you would say, okay, the first book on the shelf has 6 options, the second book's 5, the third book's 4, then 3, then 2, then 1. Only 1 book left at the end once we've arranged the other 5, right? So, but if you remember, oh yeah, when I have 6 objects in 6 positions, when I'm just arranging them all, it's factorial, then you can do it really quick on your calculator. So this one would turn out to be 720. So check to make sure you can find 6 factorial on your calculator. Okay, looks like you're still with me here. Let's keep going. Good. Maria says she's got it. I'm glad. Okay, so number of different permutations now of n different items that can be arranged when all n of them are selected. This reflects the fact that the first item may be selected in n ways, the second item n-1 ways, and so on. But it has to be the case that all n items are selected ultimately. When we're not using all n items, we just have a slightly different name for it. Instead of calling it an arrangement, we call it a permutation. A permutation is what happens if you want to make an arrangement of a set of objects, but you don't want to use all of them. Now, a combination is what happens if you want to select objects but not arrange them. You just want to pick the objects, but you're not putting them in a particular order or anything. So these are 2 variations on what we've been doing. So you're going to want to get a clear idea of when to use the fundamental counting principle, when to use permutations, or when to use combinations, and sometimes a combination of the three, and how to use your calculator to do these problems. So first, let's start with permutations, which remember is just like an arrangement, except you're not using all the objects. So the number of permutations of n objects taken r at a time, we use this notation, NPR, or sometimes you see the notation P parentheses n comma r. So as an example, let's say that we're handing out ribbons, right, for first, second, and third place, and there were 7 participants. How many ways can the ribbons be awarded? See, we could pick participant A from the 7. We could actually pick 3 participants, A, B, and C, from the 7. But that's not enough. We also have to decide, does A get first, B second, and C third? Or is it B first and C second and A third? Or what is it? So that's why we see that we're arranging or assigning a specific separate value to 3 of the participants, but not all of the participants. If there were 7 ribbons to get out, we could just say 7 factorial and be done with it. But in this case, there are 3 ribbons only. So the number of things that we're choosing from is the 7 participants. That's our n. And how many of them are we choosing? We're choosing 3 of them. So our r is equal to 3. So the notation would be 7p3. The number of permutations of 7 objects taken 3 at a time, or sometimes again you'll see it as p of 7, 3. Now your calculator actually can do this calculation, but I'm also going to show you the formula to work it out by hand, but I want to make it clear that it's perfectly fine to use the formula. Okay, so in that problem, I said it's 7p3 is the notation, but remember there's 7 ways to assign first place, then 6 ways to assign second place, and then 5 ways to assign third place. So if we wanted to, we could use the fundamental counting principle and just multiply 7 times 6 times 5, which, by the way, 7 times 6 times 5 is 210. Okay? But what I want to show you with this example is how we come up with a very special formula that works in general, where we don't have to use the fundamental counting principle to get our permutation calculation. What we observe is that 7 times 6 times 5 is the same as 7 factorial divided by 4 factorial. 7 is exactly the number of objects we're choosing from, and 4 is exactly how many were left if we took away the 3 that we're choosing. So we just write 7 factorial over 7 minus 3 factorial. Remember, 7 was our n and 3 was our r. So we have n factorial over n minus r factorial. So in general, to find the number of permutations of objects taken r at a time, we're going to use this formula, n factorial over n minus r factorial, or just plug NPR into your calculator. Okay, let's calculate it once by hand though. So if I asked you to calculate 5p3, you would recognize that for part A, that n is 5, and r is 3, and we have n factorial over n minus r factorial. That's 5 factorial over 5 minus 3 is 2 factorial. 5 factorial over 2 factorial is 60. How did I get that? 5 times 4 times 3 times 2 times 1 over 2 times 1. So we have 20 times 3 is 60, or you can just do it with your calculator. 5 factorial divided by, and then 2 factorial. Okay, for part B, I'm going to give you a minute a few seconds really to try to figure out what part B would be. Write down the formula. NPR equals n factorial over n minus r factorial. And apply this to this expression here where we have n is 6 and r is 6. Okay, so hopefully you had a chance to do the calculation, and you have 6 factorial over 6 minus 6 factorial. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And in the denominator here we have 0 factorial. Does anyone remember what we defined 0 factorial to be? So hopefully you said 1, right? 0 factorial is 1. So you're just dividing 6 factorial by 1. So it's just 6 factorial if you want to plug that in on your calculator. Now that makes sense though, doesn't it? Remember we said 6 factorial is the number of arrangements of 6 objects if you use all of them. And that's exactly what 6p6 represents, the number of arrangements of 6 objects taken 6 at a time, so all of them. So it makes sense that we would get 6 factorial, and that is 720. Okay, let me know if you have a question. All right, so here's an example. What if I wanted to find out how many 4-digit numbers can be written using the numbers from the set 1, 3, 5, 7, and 9 if repetition is not allowed? Remember, in arrangements and permutations, repetition is not allowed because you're arranging the objects. They can't sit next to themselves, right? So whenever you see repetitions not allowed, that's good. A good indication that we're allowed to use an arrangements or a permutation formula, assuming of course that we actually are trying to arrange something. Why do I know I'm trying to arrange something? Because it's a 4-digit number, and I know the 4-digit number 357 and 3,579, for example, is different than the 3-digit number 9,753. So we're definitely arranging the digits. Blank screen, huh? Oh no. Let me see what's going on. So I see that Yolanda has a blank screen. Does anyone else have a blank screen? Still streaming. The stream status is only just okay, so looks like we're having some streaming issues, but not totally blank. So Yolanda, when I post the recorded version, you could skip to the end because we're almost done, and then you'll be able to see the screen. You should be able to see it. Maria asks, so does permutation have order and factorial has none? No, both factorial is an arrangement. It's just you're arranging all the objects. So both factorials and permutations or arrangements, you can refer really to either of them as an arrangement. It's just the number of things you're arranging that varies. So there's always an order with both of those. Okay. So in this case, though, we're making a 4-digit number out of 5 digits, so we're not using all of them, and that's the distinction. So if we were making a 5-digit number out of these 5 digits, we could just say 5 factorial, but we're making a 4-digit number. So in that case, we're talking about the number of permutations of 5 things, 5 digits taken 4 at a time, 5p4. Which is going to be 5 factorial divided by 5 minus 4 factorial. And that's going to be 5 factorial over 1 factorial. Now 5 factorial is 120. And you divide that by 1 and you get 120. Okay, so both factorial and permutation, repetition's not allowed, and and the order matters. Repetition is not allowed. Not allowed. And the order matters. Okay. All right. Let's see what we have next. How many ways can you select 2 letters followed by 3 digits for an ID if repeats are not allowed? Okay, so this is a slightly different scenario. We're not allowing repetition, but that frees us up. We can still use the fundamental counting principle if we want to, but we don't have to. Because what we could do, we could do the 5-part task with the fundamental counting principle. And if we're not having repetition, then out of the 26 letters, the first letter we have 26 options, the second letter we have 25 options, the first digit we have 10 options, then 9, then 8 because we're not repeating. You multiply that together and you get 468,000. But we also could instead think of breaking the task down into only 2 parts, where we're selecting the 2 letters out of 26 and the 3 digits out of 10. So what that would look like is 26p2, because we're using permutations, because the order matters, repetition's not allowed, and we're selecting only 2 of the objects out of the 26. And then that would be part 1, choosing the 2 letters, and then choosing the 3 digits, we would have to choose 3 out of 10, so 10p3 for part 2. And notice you get 650 times 720 equals 468,000. Same value that we got doing it this way. So with the fundamental counting principle, the order still matters, but repetition could possibly be allowed. We manually adjust for whether repetition's allowed or not. But for permutations, it only works if repetition's not allowed. Okay, now let me show you how to calculate a permutation, not by hand, but on your calculator. So to calculate 17p10, for example, you're going to type the number 17 into your calculator. I'm assuming you're using the TI-30X2S. So you're going to push the PRB button PRB button is right about there. That's going to pull up your probability menu. And in your probability menu, you see NPR, NCR, and factorial. NPR refers to the permutations. So you just remember you already typed 17. The permutation option is already underlined whenever you just first log into that menu, so you just hit enter. And now you should see 17 NPR on your screen. So you type 10, and then you see 17 NPR 10. So the number of permutations of 17 objects taken 10 at a time. And then you just hit enter again, and you're going to get your answer. Now, this is a particularly huge number, and so your calculator is not going to be able to give you an exact answer. What it will give you is a number in scientific notation. So what you're seeing on your screen, if you've tried this at home, you're seeing what is referred to as scientific notation. It's some number, in this case 7.05729024, and then it tells you what power of 10 it's being multiplied by, 10 to the 10th power in this case. So let me write what that actually means. That means that it's close to the number you would get if you moved this decimal 10 places to the right. So 705729024. Let's see how many. 1, 2, 3, 4, 5, 6, 7, 8 places, 9 places, 10 places. So whatever this number is, it's very close to that. Okay, Jessica, it's okay if you don't have your calculator with you. If you want to, after, you can always go back and watch the end of the end of the video. I'm going to post a link in D2L, so then you can kind of walk through how to use this. Okay. All right. The last thing for today, I just want to mention, if the order doesn't matter, if we are selecting objects but not arranging them, that's called a combination. And you can also do that on your calculator. But the formula, I'm just going to skip to the formula. This formula for combinations is where we've taken the permutation formula and divided it by the number of ways to arrange the R objects. Because if we just do the permutation formula, we've overcounted. We've counted too many things because arrangements... Hold on. Sorry about that. Somebody knocked on the door and my dog went crazy. Okay, so what I was saying is we overcount. So actually combinations is going to give you a smaller answer because we divide by the number of ways to arrange the R objects. And we get this big funky formula. So you should practice plugging into the formula, but you can do this on your calculator as well. Let me show you. Let's say you wanted 17C10, you're going to type 17, and then you're going to push the PRB menu, and again you're going to see NPR, NCR, and factorial. So you're going to arrow over to the NCR, and you'll see 17 NCR on your screen, type 10. So you get 17 NCR 10, and notice that we get a much smaller number. 19,448, because all this is saying is if we had, say, 17 students and we wanted to pick 10 of them to, I don't know, give a bookmark to, okay, nothing distinct, nothing different, they're all getting the same treatment, but we're not picking all 17 and we're not arranging them, we're not distinguishing between the 10 in any way, then it would be 17C10. There's fewer ways to do that. Pick groups of 10 than there are to pick groups of 10 and then arrange them maybe into 10 different prizes or 10 different seats or something. So your combinations will always come out much smaller than your permutations. So I'm going to end there today. Thank you guys for attending the live chat, and we'll pick up there tomorrow morning. And I'll post the link for the recorded version of this in case you want to go back and look at it. Take care, guys. Bye-bye.